Ladies and gentlemen, please welcome Miss Laura Hayes.
Hey guys, I thought going first would be great because I wouldn't have any hard act to follow, but thanks very much, that was absolutely deadly. Mine might be more learny than laughy, but we'll see how it goes. So yeah, I'm Laura, I'm an astrophysicist and I work in the School of Physics in Trinity in the Solar Research Group. What I find when you kind of tell someone you're an astrophysics, you get one of three responses. The first one is the same way as you would say I'm a physicist, I'm a mathematician. People look you right up and down and say, oh, I always hated maths, I always hated physics. And then they kind of look to see what's actually really wrong with you. So that's what's one way. The second one is you don't really get that often, but you still get it. They say, oh, cool, astrophysics. I'm a Libra. What do you study that? That's deadly. And you're like, oh no, someday I'm going to have a bit of fun with that, but we'll see. And the third one, which I've gotten a lot recently, is people are like, oh, that's deadly, that's so cool. Like the Big Bang Theory. Oh, we're going to go to Mars. Do you think people can go to Mars? What about life on other planets? What do you think? What's a wormhole? And a really good example of that was, it was the Tuesday after lecture picnic. I was very unwell. And I was getting a taxi to Dublin Airport at 4:30 in the morning to go to Brussels for work. I was in the taxi, I was trying my very, very best not to initiate conversation. And he was like, oh, where are you going? And I was like, oh, Brussels. Oh, going for work, yes. What do you do? I'm an astrophysicist. And he like turned around, big dull, deadly, explain interstellar to me. And I was like, oh Jesus, 4:30 in the morning. So we were talking about wormholes. He was like, how did your man, that planet, when they came back, that he was real old, how did that work? So trying to explain special relativity and all that. But that's absolutely fantastic. You see people so interested in physics and astrophysics of these days. It's kind of come into our culture now. You also, into our culture now, you've got these things of doomsday things. What if aliens invade? What if we have Armageddon? What happens if another planet just shoots up and we get knocked out of orbit and, I don't know, we all die? And also, like, one thing is people are like, what happens if we align with the Milky Way? That happens all the time. We orbit the Milky Way. But things that people don't find that interesting or don't really ask the cool questions about is the sun, right? The sun is our closest star. It's not that far away, 150 million kilometers, which isn't far away in astrophysical terms. And also, it's a huge danger to us. It's probably one of the biggest risks we have at the moment as something happening in outer space is space weather. So this is kind of an almost new field. So I'm going to enlighten you today about the sun. So that's what I study. I'm a solar physicist. And the sun isn't just this big ball of fire in the sky. It's not just sitting there giving us a tan, growing our crops, giving us day and night. It's actually a really dynamic, big thermonuclear reactor, which isn't sitting that far away from us. So it's not just this big ball of fire, it's a big ball of ionized gas called plasma. So it's kind of like you can't walk on the surface of the sun. It's like a big kind of almost liquidy. And like the Earth, it has a big magnetic field. However, as it has a big magnetic field and all this plasma is trapped into the magnetic field and the sun is rotating, but it's not a solid, right? So the Earth rotates, okay, it's all together. However, the sun, because it's kind of liquidy, you have the middle rotating faster than the top, called differential rotation. And what happens is the magnetic field essentially gets twists, right? So if you're going faster here than here, it's going to start getting twisted. And as the magnetic field gets twisted, like imagine you had an elastic band, you start twisting it. Eventually it's going to snap. So what we have happen is that the sun starts rotating at different speeds, the magnetic field gets all twisted, and you get kind of like spots on the sun called sunspots of really, really high magnetic activity. And it actually is so high that it inhibits convection, so it looks cold, so they look dark. But in these regions, you can have so much twisting that eventually it snaps. Right, so you're talking about a huge, huge area of magnetic fields, and they snap. It's going to release a huge amount of energy. So this is what we call a solar flare. So it's a big burst of radiation that, of course, is coming towards Earth, it's coming towards anyway. And as you have a twist, something has to break off. So what breaks off? A giant ball of plasma. Right, it shoots out into space. And this happens all the time. And why do we care? Right? Okay, well, we're just a little planet that's rotating this big farting star. So you have to start worrying. What happens when a big ball of ionized gas hits you on Earth? So one of the nice things we have here on Earth is we also have a magnetic field. So our magnetic field, we're going to talk about elastic bands again, I guess. It's like a big ball of elastic bands. So when you have this big ball of plasma hitting this elastic band, most of it can bounce off. What happens when you have a really, really big explosion coming in? It can break these elastic bands, and essentially our magnetic field is like a dipole, so it can come in to these dipoles and essentially interact with our atmosphere. So one of the things it causes is the aurora borealis. Has anybody seen the aurora? Yeah. So essentially what that is particles from the sun hitting the atmosphere and reacting with particles. So like, for example, like oxygen might be green, or you might have nitrogen which is blue, and you're looking up, the atmosphere isn't that high, it's 100 kilometers, it's like drives a ton more, and you're seeing like solar particles hitting the atmosphere. That's one of the nice things the sun does. One of the bad things, I guess it does, is if you have like a load of like particles coming towards your satellite, it can short circuit your satellite. And that can be very, very bad for your satellites. Now you have no GPS. Another thing is that it can induce currents in the ground. So you have these particles that will then induce a geomagnetic induced current, which can go into your power grids and kind of overpower your power grids and then kind of break your transformers. So one example, like this is happening for many, many years. It's just that now we're a society so built in technology. So one of the first examples was 1859, called the Carrington event. And it was such a large solar storm that you could see aurora as far down as Cuba. So there was people living in mountains, I guess mountain people or cave people who had no social problems, or social relationship problems, I guess. And they woke up because that's what they thought it was day. It was so bright down in Cuba you could read outside. We also had the telegraph poles actually down in Valencia and Cork, where they turned them off when they were still running because there was current running through them. And telegraph poles caught fire in Scotland and places like this. So imagine that happened now. 150 years past maybe. Well, like it has, but and what's so different now? Imagine not being able to use your phone. Imagine not having any GPS. Imagine not having any power. So like trains in the UK use GPS to open their doors. So if your GPS gets knocked off, you're sitting, the station's over there and your doors won't open. Or you're in the station and the thing thinks you're over there. So this becomes a very, very big problem. So how can we predict that? And that's what I'm here to do. So we're still kind of waiting. Maybe a big solar storm is going to happen. But what we're doing every day now is to try to understand why these things happen. Why is a solar flare going to happen? What causes it? What are the prerequisites to happen? So at the moment in our space weather forecasting, we're still kind of back in the day where the guy in New York would call the guy in Chicago and say, what's your weather like there? And he'd say, oh, it's snowing. And they're like, oh, dead, it's going to snow in New York in 2 days. And we're still like that in space weather. So now what we're trying to do is try to understand these things, when are they going to happen, when are we going to look at them, and when we're going to see when they're maybe arrive. So maybe we'll have like 2 days to kind of say when they're going to come. And that's all I have to say.
Laura Hayes, everybody.